Okay, so the next thing that we will talk about here, and then after that we have almost nothing related to these transistors, except that there is still a lot left related to transistors. Of course, you know that transistors is a long story. It has taken many years, probably, I don't know, since 1950 we've had basically at least, I suppose, 57 years of history behind transistors, and there is all different types of transistors. But the basics are not that complicated, of course, once you understand them. So now what we will do is that we will talk about there is a condition called saturation. We have talked about this before. Now, what this saturation is that basically in the previous circuit that we had before, we had some V of C, which was the voltage across the collector and the emitter junction of the transistor, and we managed to set that voltage to different voltages. As you saw in the previous video, we set that voltage to 5 volts, then to 2.5 volts, and then to 7 volts, and so on and so forth by changing the values of I of B, I of C, R of B, R of C, and the beta, and so on and so forth. So using those three things, you have control over the voltage drop across the PN junction of the collector emitter junction of the transistor, right? Now there is a condition that, now suppose that you have this circuit over here, and this is your collector, this is your emitter, and this is your base resistor, and this, suppose that I give it to a power supply, and this goes to ground and to the emitter, and then your collector goes through a resistor, goes to the positive supply voltage. So suppose that this is your circuit, and V of C is basically over here. So this is basically the positive rail, and this is the negative rail of the supply, and whatever V of S is, basically then there is some voltage drop across R of C, and there is some voltage drop across the PN junction, and that becomes the full power supply voltage. Now, if you can, and this is V of S, right? Now, if you can create some, there is some beta related to this transistor that you already know. If you can create a condition in which basically you can create enough basically base current, and as a result of that create enough collector current, as you saw before, the more collector current that you have, the less voltage drop is going to occur at V of C, right? And then the higher the collector current, it basically acts like this, meaning that you know that beta, your beta is equal to I of C to I of B, right? So that means that by increasing I of B over here, and this I of B you can increase by, if you basically apply the Ohm's law to the resistor over here, V is equal to IR. So if I keep this voltage constant here, by decreasing the value of R, the current is going to increase, right? So the current is going to increase here, meaning that the less the value of the resistor here, the higher is going to be the value of the current. The higher the value of the current, and then you put that value of I of B in this relationship, beta is equal to I of C to I of B, then basically the higher the value of I of B, the higher the value of I of C, because this is a ratio and the ratio has to remain constant. So then you have the higher the value of I of B. The higher the value of I of C, right? So that's the current going through this part over here. So now again, applying the Ohm's law, for example, to this resistor over here. If I assume that I'm keeping the value of this resistor constant, the higher the value of I of B, the higher is going to be the value. The higher the value of I of C, the higher is going to be the value of V of the voltage drop across this resistor, and the higher the value of the voltage drop across this resistor, the lower would be the value of the voltage drop across the PN junction of this transistor. And so logically you can say that the higher the value of I of B, the higher is going to be the value of I of C over here. The higher the value of I of C, again, the higher the value of the voltage drop over here. And the higher the value of voltage drop over here, the lower the value of voltage drop related to V of C. So that means that by increasing the value of the base current, you are going to decrease V of C more and more, and then by decreasing it more and more, meaning that the V of C is getting closer and closer to zero. So that's basically the whole story here. And there comes a point where basically your V of C would be equal to zero. When your V of C is equal to zero, that condition is called saturation. And basically when V of C is equal to zero, basically the collector emitter junction of your transistor is acting like a closed mechanical switch, meaning that you have your power supply over here. And then you have suppose that this is the PN junction of the transistor, or the collector emitter junction of the transistor, and suppose that you have, for example, some load over here as well. And if I close this mechanical switch like this, then of course a closed mechanical switch has 0 volt voltage drop across it, and that 0 volt voltage drop is basically the voltage drop over here, right? The 0 volt voltage drop over here, and then your load gets the full power supply voltage over here. Otherwise, if I open the switch, then basically your load gets no power from the power supply. And so when your transistor goes into saturation, meaning that when V of C is equal to 0, then the collector emitter junction of the transistor acts like a closed mechanical switch. A closed mechanical switch basically acts like this, and then that way you can say that your transistor has gone into saturation, right? So that's basically the whole story here. Now we want to know how we can actually do that. Of course, you already know how to do that by increasing the base current, by giving enough, by providing enough base current, you can you can essentially make the V of C equal to 0. So that's pretty simple. So now let's consider the same example that we had before. And in that example, what we had was that basically we had a 10-volt power supply over here, and we had a 100 kilo ohm resistor over here, and we had a 1 kilo ohm resistor over here, and we had a beta is equal to 100 over here, right? Now let's calculate basically V of C in this circuit and see what we get for V of C in this circuit. So in this circuit, basically you have this R of B over here, and this R of B is 100 kilo ohms. So that means that the base current over here would be, if I assume that all of the power supply voltage is dropped across R of B, then basically applying the Ohm's law to R of B, I will have basically the voltage drop across R of B is equal to the power supply voltage. That means that 10 volts is equal to I, the current going through the resistor is I, and the resistance is basically 100 kilo ohm, which is 100 into 10 raised to the power 3 ohm, right? Which means that I is equal to 10 volts divided by 100 times 10 raised to the power 3 ohm, which is basically 10 raised to the power negative, this is 10 raised to the power 4, which is 10 raised to the power negative 4 amps. So that means that I of B in this circuit is equal to 10 raised to the power negative 4 amps. Again, I'm not going to bother about milliamps and microamps and that sort of thing here, because that would get in the way of calculation. When you're doing, it's just not easy for me to do that. Some people find it easier to think in terms of milliamps and microamps and that sort of thing. But then in that case, basically your numbers are not exactly scientific numbers, meaning that you get, for example, 100 milliamps or 95 milliamps or 85 milliamps. That's perfectly okay when you're working at the bench. When you're working at an electronics bench, I do the same thing, because over there I'm not doing much calculation. I'm doing everything in my head. And I know, for example, I have intuitively, I know what is 100 milliamps, what is 50 milliamps, what is 2 amps, what is 3 amps, and so on and so forth. But when I'm calculating things, I'm not working at the bench. It's not easy to do calculation that way. So you have to choose the right mode of the right way of doing things at different times, of course. So now my base current is 10 raised to the power negative 4 amps, right? So then as a result, I know that basically, since beta is equal to I of C to I of B, and since beta is equal to 100, and therefore I of C becomes, this is 10 raised to the power negative 4 amps, therefore I of C becomes 100 into 10 raised to the power negative 4 amps, which is the same thing as 10 raised to the power negative 2 amps, right? So I of C becomes 10 raised to the power negative 2 amps. And it makes sense because as you can see, if you take I of B and multiply it by 100, you'll get I of C, which is 10 raised to the power negative 2 amps, right? So So that's basically that. Now the voltage drop across this resistor, if I apply the Ohm's law, V is equal to IR to this resistor over here, what I will have is that basically the voltage drop across here is going to be basically I, which is 10 raised to the power negative 2 amps, times the resistance, which is 1 kilo ohm, 10 raised to the power 3 ohm, which is the same thing as 10 volts. So that means that the voltage drop across this resistor is 10 volts. So V of R of C is equal to 10 volts, right? And of course, you know that basically the whole power supply voltage was also 10 volts, right? So that means that the whole power supply voltage is being dropped across this resistor, meaning that there is no voltage to be dropped across the PN junction of the transistor, which in turn means that V of C is equal to 0 volts. And this condition is called saturation. And now in this condition, the PN junction of your transistor is just a mechanical switch that you're closing and opening. As long as there is base current, you are closing the switch. As long as there is no base current, you are opening the switch. And that's basically the whole story behind saturation. And so as a result, you can compare the same circuit, basically this part of the circuit, you can compare it to a switch like this, meaning that you have the 10 volt supply that you have up here. This is the 10 volt supply up here. And then you have a 1 kilo ohm resistor over here. And then you have basically this V of C over here. And then you have this PN junction of the transistor that is now acting as a switch, that is now acting as a closed mechanical switch, and then this goes to the ground, right? And that's basically your circuit right now. And now you can say that the transistor is turned on. Or they also say that the transistor is on. Both of them, both are actually correct. So that's basically the whole story behind saturation. Now, if we have enough, if we get if we have the opportunity, I will also go over to the bench and probably show you a couple of things with transistors on a breadboard, but it's not easy for me because basically my different types of things, for example, there is multimeters over here and over there, and then when you're working with these transistors, you have to monitor a few things simultaneously, meaning that you have to monitor some voltage and some base current and some collector current and some resistance and so on and so forth simultaneously, and then essentially everything had to fit in the shot simultaneously. And so there has to be, you have to have all of these little multimeters that you put next to one another, and then put the circuit next to that, and then put all of them in the shot so that everything is done simultaneously. But of course, if you want to do anything in electronics, you have to you have to actually do this on your own, meaning that you have to take a couple of transistors, a couple of multimeters, a simple power supply, and things like that, and a breadboard, for example, and then put the circuit together yourself and measure all of these currents and voltages for yourself and see how that works out for you, because of course the theory is nice, but then I suppose if you want to do anything with electronics, of course you have to have your own tools as well, right? Now there is also a couple of things related to the JFET transistors, junction field effect transistors. I'm not going to talk about that here because it's not really relevant. We will talk about that wherever basically it's necessary. And so I'm going to end this video here. In the next videos, we will talk a little bit about a couple of examples related to basically these NPN and PNP transistors. So I'll see you in the next video, and thank you.